Hello, in this video, let's discuss the series shunt feedback. So what I mean by series shunt feedback is essentially I am sampling an output voltage, right? And I'm adding it as a voltage in the feedback. So if I look at the circuit, let's look at an open loop amplifier which looks something like this. So I have an input voltage which falls across the input resistance of the amplifier. That generates an output voltage which is A times the input voltage, and then it has an output resistance R naught, right? And an output voltage that is V naught. Now what the feedback signal does is the feedback network samples this V naught, right? So it's a shunt feedback. So it's sampling the output voltage and generating a feedback voltage which is beta times V naught. And this voltage is sent in as a series fashion with the Vs. So if you look at Vi now, Vs is going to drop essentially across Vi and Vf. So Vf is going to steal Vs away from Vi, right? So that's the negative feedback. So this is what is the simple topology of a series shunt. So again, I have a voltage amplifier. A is a voltage amplifier. My beta network is sampling a voltage and returning a voltage back. And ideally, if you look at the feedback, post feedback, I can represent this entire circuit, or my goal is to represent this entire circuit as a voltage amplifier with some input voltage Vs, some output voltage V naught, with an input resistance which is given by RIF. Now that is Ri with feedback, and an output resistance given by ROF, or the output resistance with feedback, and the gain essentially given by AF. So let's try and first work out the numbers for ROF, RIF, AF, etc. Now if I look at the input resistance and the output resistance with feedback. Now V naught upon Vs is AF, and that's given by A by 1 plus A beta. Now Vi is nothing but Vs by 1 plus A beta. We looked at it when we did the signal flow diagram. And so if I look at II, that is the input current is given by Vi by Ri, and that's going to be given by Vs divided by Ri plus 1 plus A beta, right? So with feedback, the input resistance, right, increases, which was initially Ri, now goes up by 1 plus A beta times Ri. So Rin essentially increases with feedback. And if you think about a voltage amplifier, in a voltage amplifier, you want your Rin to be as high as possible and you want your Rout to be as low as possible. So what feedback is doing is feedback is increasing the apparent input resistance that happens in the circuit. So to measure Rout, we use the techniques we've used time and again in the course. We short the input, apply a voltage at the output, and measure the current at the output. So when we do that, what we get is Ix is Vx minus A times Vi by Ro, right? And Vi is equal to Vf. In this case, because my Vs is 0, my Vi is nothing but minus Vf, which is minus beta times Vx, which gives my Ix to be Vx into 1 plus A beta by Ro. In other words, my output resistance because of feedback reduces by an amount of 1 plus A beta. So again, this 1 plus A beta is an important term. It's kind of the amount of feedback they've applied to the circuit, and it dictates how much the increase in RIF is and how much the decrease in Rout is. Now let's look at what happens because of loading. So previously we've looked at cases where this beta network is not loading, right? But in reality, when we apply a circuit, when we use a circuit, this circuit will have its own input resistance and output resistance. If I look at this, I have a signal flow that flows in through this node 2. So this feedback network presents an input resistance to this node here, and this feedback network also presents an output resistance to this circuit here, right? And so what you see here is that the feedback network loads both the input, the output and the input by its input resistance and its output resistance, right? So to find the beta, what we need to do first we just look at the feedback network, identify the feedback network, apply a voltage at node 2, measure the output at node 1 when 1 is open circuited. And so this beta is essentially the gain from node 2 to node 1 when node 1 is open circuited, because I'm sending it as a voltage. Now once I've done that, my next step is to find the input and output resistances. So remember, in the feedback network, the input of the feedback network loads the output of the amplifier, and the output of the feedback network loads the input of the amplifier, right? And so to estimate Rin, what I need to do, that is how it's loading the output of the amplifier, I need to estimate what is the current I see, what is the resistance I see looking into this node, and that I can do by ensuring that this output node is open. I apply voltage at the input of the feedback and measure the input current, right? So that gives me the effective resistance that's loading the output. And so that is going to be given by V2 upon I2. Now similarly, when we want to do the R out, this is similar to a voltage amplifier, right? I want to find what is the output resistance. To find the output resistance, I need to short the input. That's what I do. Apply a voltage at the output and measure the output resistance. And so that gives you essentially R out, which is V1 upon I1. Right? So now once you know what Rn and R out of the feedback network is, let's call them R22 and R11. Then what essentially the circuit boils down to is, if I look at the main circuit, my R22, which is the how the feedback network loads the output, it loads it as a resistor in parallel to RL, and my feedback network appears as a series resistance at the input, right? So when I estimate R22 and R11, and then I can go about and solve the circuit and estimate the various properties. And so this A, or the open loop gain of the circuit, can now be estimated as V0 upon Vs. So remember, to estimate this open loop gain, I need to first understand how my feedback network is loading both the output and input. Otherwise, I'm going to estimate the wrong value for A, and hence estimate the wrong value for A beta, and hence get all wrong numbers for my input and output resistances. Right? So once you know A and beta, then you can calculate the loop gain, and then you can calculate the impact on the various parameters of the circuit. So let's look at a couple of examples. So here I asked to find the loop gain and feedback factor of the circuit. So let's first understand what the circuit looks like. So here I see a common source amplifier made up of M1 and RD1. I also see another common source amplifier made up of M2 and RD2, right? Now what's happening here is this output of the second common source amplifier is sent through a voltage divider or a resistive divider bridge, and that feedback signal is sent as the voltage at the source of M1, right? So this is the summer, if you will, the signal summer that is being implemented here, and this is your feedback network. So first things first is to identify the various components. So we have the signal summation right there happening as a VGS, and the feedback network essentially consists of this resistive bridge. So let's first find, so this is my feedback network. My output voltage is here, my feedback signal is here. So beta is very simply written by R1 upon R1 plus R2, because that is Vf divided by V0. Now we need to find the loading. Now again, this is a very simple circuit, it's a resistive circuit. So let's look at the loading. Now if I want to find how this circuit loads the output, what I need to do is keep Vf open and measure the current flowing in V0 via this feedback network. And I see that the current flowing flows through both R2 and R1, which means that the feedback loads the output as a combined resistance of R1 plus R2. Right? And now if I look at how the feedback network loads the input, now to do that, I take the feedback network, I short its input, so my R2 is connected to ground here. This is my feedback signal, and I want to measure Vf upon If. And what I see here is that the feedback network loads the input as R1 parallel R2. So now that I estimated what the load resistors are because of the feedback network, to calculate the value of A, I will basically redraw the circuit by breaking the loop there and attaching my R1 plus R2 as a load for the output, my R1 parallel R2 as a load for the input, and then I want to measure V0 upon Vn. Now this is a circuit you've done time and again. This is a common source with source degradation. This is a regular common source circuit. Again, to keep things simple, if I assume lambda is equal to 0, Then the first stage is going to be given by GM1 RD1 by 1 plus GM1 into R1 parallel R2. Gain of the second stage is GM2 into RD2 parallel R1 plus R2. So remember, this feedback network is loading it. If you'd assumed the feedback network was not loading anything, then mean numbers you would have gotten wrong numbers for the gain. And so your open loop gain is going to be given by the product of these two gains. Now let's look at another circuit here. Find the loop gain and output resistance for the circuit at low frequency. So here I have a differential amplifier, right? Now the output is taken, sent through two capacitors so it's a capacitor bridge here, and that output is being sent to the input here. So again, the summation happens as M1 minus M2. So if you look at the feedback network, it consists of C1 upon C2. And so now if I look at beta is essentially VF upon V naught. So it's a low frequency. Remember, it's given low frequency, so I can assume this essentially to be a DC kind of a setup. And so I'm looking at the voltage distribution across C1 and C2. So my beta is going to be given by C1 upon C1 plus C2, right? So at low frequencies, the caps may be considered open circuit. Okay? Now once I do that, now I need to find, and again, because they are caps, they are not going to load my circuit, right? Because they're not going to pull any current. If you're not going to pull any current, essentially this feedback is an ideal feedback because it has infinite loading at both input and output. So if I look at A now, my open loop gain is simply the gain of the differential amplifier, which is GMN into R1 parallel ROP. My beta is C1 upon C1 plus C2. And so therefore the loop gain is going to be A beta, which is this GMN into R1 parallel ROP by C1 plus C2. And the output resistance can be given by applying the formula R out divided by 1 plus A beta. And so for large loop gain, when this A is very large, I can write AF as 1 by beta, and my ROF simply becomes dependent on the capacitors and 1 by GM. So because of this feedback, now remember, the diff amp had a problem of a high output resistance because my output resistance was dominated by the output resistances of M2 and M4. By doing the feedback now, I've brought it down to be similar to a common gate amplifier, right? So 1 by GM close to common gate. What I've done there is I've traded off the gain for the output resistance. Let's find the input resistance at low frequency. Again, using the same logic. When you do capacitor bridges like this, the capacitor bridges don't load the circuit. So it becomes very easy to find beta because essentially you can look at it apart. So my beta is going to be again given by C1 plus C2, right? And this is again a common gate circuit. And what are we doing here? The common gate circuit, I'm applying a feedback signal to the gate. So I'm doing the same thing as a summation where instead of applying the feedback signal at the source, I'm now applying the feedback signal at the gate, right? So again, my beta is going to be given by C1 plus C2. My gain is GM times RD, again assuming lambda 0. So my A beta is given by this. Now remember, input resistance of a common gate amplifier is very low. It's normally 1 by GM. Now with this feedback, what happens is my Ri into 1 plus A beta, or I essentially get as 1 by GM into 1 plus GMRD by C1 plus C2. And if I assume that this term is very large, my input resistance essentially becomes similar to RD. Right? So what is happening is because of feedback, I'm able to again, this common gate amplifier is able to provide a very high input resistance, which is what is needed in an ideal voltage amplifier. Thank you.